So we have seen buffer solutions and we have done enough calculations as far as buffer solutions are concerned. Now let's talk about hydrolysis. Let's see how the pH is going to be determined if no excess acid, no excess. For instance, you are titrating. Let's talk about this. You are titrating a strong electrolyte. Maybe it's a strong base such as sodium hydroxide. Okay? And you are titrating it with a weak acid, maybe CH3COOH. Or you are titrating a strong acid such as HCl and you are titrating it with a weak base such as ammonia. That at end point, when all acid has reacted, all base has reacted, at that point, at end point, how are you going to determine the pH of that solution? And the pH is it going to be neutral? Is it going to be 7? Is it going to be above 7? Or it is going to be below 7? And so that one can be determined using this concept of salt hydrolysis. So what is salt hydrolysis? Hydrolysis refers to any reaction where water participates as a reactant. Now in this case, water is a reactant. Okay? However, still it's a solvent, so it is still in large excess. So with salt hydrolysis, therefore, it is a process whereby a salt that is dissolved in water produces cations and anions which interact with water to produce hydrogen ions and OH ions. You remember in organic chemistry where we talked about aluminium chloride, for instance, and we say that the pH of this salt is not 7, but it is below 7. This is acidic. So similarly with these weak acids and weak bases, when they are reacted with water, when they are dissolved in water, the ions, they will ionize food since they are strong electrolytes. And the ions formed, they can react with water to produce hydrogen ions or hydroxyl ions, which will lead to a decrease in pH or an increase in pH, depending on which ions have been produced. For example, take an example of this. Take an example of, for example, ethanoate, sodium ethanoate, which is CHCOO and then sodium. Okay? Sodium ethanoate. Now, when this sodium ethanoate is dissolved in water, okay, this is solid, aqueous, it is dissolved in the water, it will fully ionize to give us ethanoate ions, CO minus aqueous plus sodium ions. Now for sodium ions, they are large cations, and so they cannot hydrolyze. Don't forget your inorganic chemistry. But now for these ones, these ethanoate ions, they can still react with water molecules. Okay? Ethanoate ions, they can still react with water molecules, aqueous, because remember it's a solvent, and in this case water is in excess. Okay? They can react with the solvent molecules, okay, to form a weak acid, okay, which is ethanoic acid, aqueous, and in the process, the OH ions, they will be produced, aqueous. And so the resultant pH of this solution, instead of it being 7, because of these OH ions that are produced, the resultant pH is going to be above 7. Let's talk, how about for a base? Let's consider a salt of a weak base, such as maybe this, okay, ammonium chloride. Let's not complicate things. Ammonium chloride. It will also dissolve in water, aqueous. It will dissolve in water and food to give us ammonium ions. Okay, ammonium ions plus the chloride ions. Now, like I told you, the chloride ions, they are large in size, so they cannot hydrolyze. But the ammonium ions, they can hydrolyze by reacting with water. Okay, this is ammonium ions plus aqueous. They will react with water, since water is a solvent and water is in large excess, okay, to form the ammonia solution, okay, aqueous, and hydroxonium ions, H3O plus. And this equation is good. Why good? Because it shows that water is, in this case, water is a base. It is reacting as an electron acceptor. So now, because of these hydroxonium ions formed, because of these, it's the same as hydrogen ions. So because of these hydrogen ions formed, the pH of the resultant solution is going to be less than 7. Is going to be less than 7. And by the way, from this, you can determine the hydrolysis constant Kh, which is simply the concentration of hydroxonium ions formed times the concentration of ammonia that is formed, everything divided by the concentration of ammonium ions. As simple as this. As simple as that. So let's proceed. So now, the hydrolysis of a strong salt and a strong base, and we have already talked about all this. You have a strong base and a weak acid, for example, sodium acetate, sodium carbonate, and sodium cyanide. They will still ionize, okay, to form. I've already explained this. So the salt being a strong electrolyte to highly dissociate to produce that one, and then more water molecules, they will ionize to restore the equilibrium, producing more hydroxyl ions in excess. So the solution will have a pH of greater than 7. And I illustrated that. So now let's see how the hydrolysis constant is going to be determined. And let's consider such a salt of ours, which is formed from a weak acid, Ha, and a strong base, BOH. So our salt, let's divide the board. Our salt Ba, okay, I can say solid, it will dissolve in water, aqueous, to produce B minus. Okay, this is B plus because it is formed from a strong base, and this is aqueous, plus A minus, and this is minus because it is formed from a weak acid. Okay, now the A minus, they will undergo hydrolysis. Okay, they will react with water molecules like how we illustrated it above to produce, we use half equations to produce B, sorry, it's A, sorry for that. So here we shall produce Ha, and this is aqueous, plus the OH. And also this is aqueous, and this is negatively charged. Now the hydrolysis constant of such a reaction, which is KH, is simply the concentration of undissociated acid, okay, HA, times the concentration of the base of the OH ions that are produced in this reaction, everything divided by the concentration of the ions, okay, which is A minus. Now, you would have put water, but here water is in large excess. Since water is a solvent, then the water is in large excess. And this is our expression for Ka, for KH, or hydrolysis constant. If you want the pH of this solution, we shall simply get the concentration of OH ions, okay, and we make it the subject of the formula, which is simply KH, and the KH is the hydrolysis constant times the concentration of A ions, and the concentration of A ions, it is the concentration of the salt that was used, that was dissolved. Everything divided by the concentration of the undissociated acid, okay, times, yes, simply that one, simply that one. But remember, at equilibrium, these two are equal. At equilibrium, the concentration of undissociated acid is equal to the concentration of OH. So the concentration of OH is equal to the concentration of undissociated acid that has been formed. Okay? So this is the same as OH squared. Okay? OH squared is equivalent to the KH times the A minus. Now you have this, you have this. So what will be the concentration of OH then? It is simply the square root, okay? The square root of KH, the product of KH times the concentration of the salt that was added. So if you want the pH, you can get the POH, and then after you get 14 minus the POH. So as simple as that. Not so, guys? Yes. Now the relationship between KH, Ka, and Kw. Now from the expression that we have for KH, I mean this very expression, this one, okay? So from that expression of KH, which is equal to the concentration of undissociated acid times the concentration of OH ions that are produced, everything divided by the concentration of the base of the A minus ion. Now if we multiply the concentration of hydrogen ions, both sides up, concentration of hydrogen ions, okay, here and here, it has no harm. There is nothing that has changed, because concentration of hydrogen ion, this is the same as 1, and if you multiply this by 1, it remains the same. Nothing has changed. Okay, are you able to see that? Now from this, there is no harm if I write it as this. My KH, there is no harm if I write it as this. I write the concentration of HA, undissociated acid, out of the concentration of A minus, okay, times the concentration of hydrogen ions. Everything, this is a dot, Okay, let me say times the concentration of OH. Are you seeing this? Times the concentration of hydrogen ions. Still, this is still the same thing. And there is no, it is still the same thing. Are you seeing that? Yes. Now, if you remember from where we began from, are you aware that Ka is, if you have such a reaction, the acid Ha, it will dissociate to give us hydrogen ions plus the A ions. This is side 1. So if we are to get the Ka, are you aware that it is the concentration of hydrogen ions times the concentration of A ions, everything divided by the concentration of undissociated acid? Are you aware? Do you agree? Yes. And also for water, are you aware that water has this equilibrium? Water has this equilibrium concentration of OH. Oh, sorry. It will ionize to give us OH ions plus the hydroxyl ions. Okay? Sorry for that. Sorry for the states. Okay, let me rub it because you know students, if you don't rub, they will write that very thing. So are you aware that from this I can get the Kw as concentration of OH ions? You agree? Divide by, sorry, times concentration of hydrogen ions. Okay? Divide by the concentration of water. But since water is our solvent, then its concentration, it is in large excess, so that its concentration is assumed to be unity. So therefore, our Kw is simply this. So now, what I've done, have I changed anything? No. So, do you agree that this is actually Kw? Do you agree that actually this one is the same as Kw? Yes. So, if I put Kw up, and you see this, are you actually seeing this as the same as 1, the inverse of this? Are you seeing that it's the inverse of this? So are you seeing that this is 1 out of Ka? Do you agree? Yes. So am I wrong to write my Kh as 1 out of Ka times Kw? No, I'm not wrong. So am I wrong to conclude that therefore my Kh hydrolysis constant is equal to Kw out of Ka? And this equation, we shall use it frequently in the preceding examples that we shall do. This equation, it is so important as far as hydrolysis is concerned. So you can practice this example. Oh, not an example, but we are going to stop here. And in our next lesson, we shall start from there.